Ronan is going to enlighten us a little bit about ESI and what they do, and Badri is going to be talking about how they're developing and how they work with the casting industry and what's going on in state-of-the-art in simulation technologies. Ronan is Technical Support Manager in the UK, and Badri is Product Marketing Manager for the Casting Solutions based in Switzerland.
Firstly, I'd like to thank Angela for the introduction and also chairing the session this afternoon. Secondly, good afternoon, everyone. I think it's, as Angela explained, it's important to recognise Badri is the main event in terms of our presentation today. He's going to talk about simulation in casting, and this is perhaps what you're all here for. But I'd like to perhaps explain a little bit about ESI, the company we work for. Very often in the industry, people know and understand the products we sell, but very often they don't know about ESI, the company. Now, I'd like to apologise. I'm going to really fly through less than a handful of slides because Badri is perhaps the main event, and if I can just keep as brief as possible in giving you the presentation about ESI, the company we work for. I think it's important, first of all, to recognise the importance of the environment and how these technologies are very much enabling technologies in terms of lightweighting, in terms of lower emissions and energy consumption reduction. Professor Mark Jolly was speaking last night, and I guess again today about a sustainable industry, sustainable environment. So it's a good place to start. Quite quickly, if I explain ESI as a tech company, we all know what tech companies are now, but we've been around for 40 years. Back in the mid-1970s, we were the first company to do a full-scale structural crash model with Volkswagen. And if I lead on from that, we are innovators in the industry. Other software companies tend to copy a lot of what we do. But finally, I mentioned Industry 4.0. You'll all have heard the buzzwords about data analytics, machine learning. This is the future of where our company is evolving. Yesterday, Badri and I were in Manchester. Interesting enough, that's probably where Industry 3.0 kicked off. So it'll be interesting to see how we go forward with Industry 4.0. So what do we do as a business? So if I mention, you're all aware that in the industry, not just casting but engineering and in general, there are a whole variety of trades and applications, disciplines. Now ESI tries to cater for as many of these as possible, and so we've evolved this kind of almost like ecosystem of products. So starting with casting, the casting trade in general and simulation of the casting process, which Badri will explain in more detail. Sheet metal forming, composites manufacturing, welding and assembly, NVH and dynamics in automotive and aerospace, comfort, occupant comfort in aerospace and automotive, biomechanics. So big part of our business is in automotive body and white, crash and safety, stiffness, vibroacoustics, acoustics in the occupant cabin, fluid dynamics and multiphysics, electromagnetics. You know about autonomous cars and radar and sensors, but also multiphysics. So we are experts in materials and physics. Yeah, that's our core of our business. So you can see we cater for a wide variety of trades and industries. In terms of future development, we're looking at co-collaboration, systems modeling, not 1D modeling, and then virtual reality. Finally, if I just quickly recap, you have manufacturing solutions, end-to-end solutions, performance, in-service performance, virtual environment, data analytics, integration, virtual reality, cloud, engineering services, and just to give you a few references, hopefully I didn't take too long, I'll hand over to Badri, and thanks.
Thanks, Ronan. Hello, everybody. In fact, Ronan could have well made my part of the presentation as well, but because I was here, so he was kind enough to give me this slot. So I mean, this was the first slide to start with the typical foundry industry challenges. I don't think I need to speak to you guys, so you very well know. But the idea over here was to like to talk about the presentations. To talk about, I mean, the focus will be on automotive components, die casting, and then the idea is to say that there are various challenges which the foundry industry is facing. So we are focusing on trying to provide a tool which is going to help predict defects in advance, to trying to move the manufacturing to the left, so that we do things in advance. So when we talk about die casting, so it's important to start with the right die temperatures. So here you see the die, not just the die, but also the holder, all the inserts. So everything is modeled first, so that we get the right operating die temperatures. And then there are several aspects which is happening during the shot. For example, let's say the spraying. So this is also a very important part. So it's possible now to also model the spray header, also the blow, the way it's done, or the way it's happening on the die casting machine. All is done so that we are able to align, in fact, the simulated die temperatures with your real die temperature. Sorry. So to be able to align what's captured on the thermal image, same way also to look what's happening in the simulation. So when we have this right, then we go for the filling simulation. So as we saw in the morning, Professor Campbell's presentation, I mean, so everything, all the oxides, everything happens during this kind of chamber filling. So it's very important to consider this, and then to make this, to study what's happening during the first phase, and then everything gets translated. Any problems which are over here gets translated into our cavity. Okay, it's always 2 clicks at a time. So we can also, I mean, once we make the simulation, we can quickly go for a quality dashboard. So let's say I call this as a filling quality dashboard. So there could be several contours which one can study. So here the idea is to just focus on the air entrainment. So we see what are the regions where you have the air which is entrained. We can also look at the oxides, the regions where the oxides are at very high level or unacceptable level. And then finally, also what is the pressure which is requested, and based on this, one is able to also select the machine. So as we talk about this machine selection, I would just like to switch a bit onto one case. So this is in fact coming from one of our customers, which is FAR, so who was producing this automotive oil pump for BMW, and BMW wanted to rework their contract. So which means that price would be a question. And what would it mean is like FAR needed to think about modifying the process so that they still have their bottom line. And one classical approach, or what everybody is always doing, is try to go from single cavity to double cavity. So they were producing the single cavity one on a 560-ton machine, and when they calculated, it seemed that what was required was a 1200-ton machine. But in fact, they did not have a 1200-ton machine. So they wanted to ensure if this was really required, but by means of simulation, and then really invest. So this is why the discussions came to us, and we discussed together with our Italian colleagues. And finally, what was done was it was produced on a 750-ton machine. So the simulation was able to consider the aspect of the machine, and to say that you don't need 1200 ton, but it can be produced on a 750-ton machine. And how was this in fact achieved? Was to link ProCAST with the die casting machine. And over here we were discussing with Colosio because of the ecosystem. So Colosio was quite near, so that was a machine also in question. So what was done was first to integrate the machine database inside simulation software. So then the simulation software knows what is the machine, what is the pressure, or what is the maximum pressure available on the machine. And then you know what is the operating point or operating zone of this machine, just like what's happening during on the die casting machine. And then you translate this information onto the solver. So then the solver knows what is the maximum pressure which is available on the machine. And as soon as it increases above what is available for this particular machine. So the piston kind of, slightly reduces the speed, which is what is happening on the machine. And then it's also possible to export this optimized velocity profile back onto the die-casting machine. So this was also in fact recognized at last year's METAF, which is an exhibition in Italy, and ESI along with Eco3 and Colosio, we were recognized for this innovation award. So as we are through with filling, so the next thing is certification, and most classical defect in a casting process is in fact the shrinkage porosity. So it's important to have a good shrinkage porosity map in alignment with what we see on the CT scan. But not only that, but also to be able to in fact quantify the porosity. So it's also possible to know exactly what is the volume of porosity what you have. And if required, you could also transport this porosity, let's say, on your machine CAD model or machine final model, just to understand what will happen if you still have porosity and if the machining is going to reveal this porosity. So on some machines, we also see that there are some squeeze pins which are available. So it's possible to model squeeze pin. So to determine at what time it should be activated, what should be the size of the pin, what should be the distance which it needs to be pushed, and to finally predict what happens without and what happens with, what will be the quality of the part. So this is just a few contours again, just to understand what is the performance. Let's say we call it as a performance dashboard. So one is the as-cast properties. So it's possible to predict the as-cast properties. The die life, which is very important. If the die is not working well, then if the shots are getting reduced, so then it's also a cost because we need to produce another one. And then finally the residual stresses, which is something which cannot be avoided in the casting. So this is quite an important phenomenon which is occurring because of the thermal imbalance. And the outcome of residual stresses is in fact the deformation. So there are different ways to measure the deformation. So it's very important to measure the deformation well, because simulation is as a model. So you have the shrinkage effects compared to the CAD. So there is the cavity is bigger than the CAD, and you have the dies. So the die has a thermal expansion. So all these needs to be considered well to evaluate the deformation. So one such thing, I mean, what everybody is using is like 3D scanner. So we have the part which can be measured and quickly, you get all these 3D points which can be put into that. And what we did was based on the request what we had from the industry. So ProCAST software simulation results, and the deformed part or the as-cast part from simulation can also be input. So which means we superimpose the measured casting, and we take the simulated one, and then quickly we can evaluate what are the regions which are not in line with how it should have been, and is it too big or is it too small. So for example, here we see so that the tolerance is quite high, which means that there is a slight deformation. So what we saw is somehow we followed a process chain. So starting from the thermal cycling inside the casting cavity, filling certification, and finally we came out of the final shape and dimensional control. So there are several aspects which can be studied. I just picked a few things which I thought could be of interest. So the same thing can also be done for another casting process, a sand casting process or an investment casting process. So before I end my presentations, I have a couple of slides more, but I just switch to a sand casting. Though the presentation was on die casting, I just wanted to choose another process because I see that there could be an audience which is also interested in sand casting. So here is a casting. Make a simulation of the casting. So the feeders are designed, and this is a porosity map, and it seems that there is no porosity inside the casting. But when we go on the shop floor, there is every possibility that there are certain process parameters which are going to vary. So here is an example just to study the robustness. What happens when one of the process parameters is going to vary on our shop floor, which is in this case the casting temperature. So what is, I mean, this is the value which is considered, above which is the casting is not acceptable, and below which this is acceptable. So this should be in line with each of the casting quality requirement. And over here, what we see is like when we reduce the casting temperature, so it seems that the porosity is going to increase simply because it's not able to feed. After a certain while, when we also increase it, the porosity seems to be out of range. So which means that through simulation we are able to specify what is the process window for the casting temperature. So if the casting temperature is inside this window, then one can go ahead and manufacture. So then we will still be in acceptable range for the defined quality. On the same example, so let's say we are not just varying the casting temperature, but also the amount of metal which is poured inside the cavity is going to vary. For the sake of simplicity, I have not taken all the simulations, which was all the results of the simulation, but what is done here is just two cases. So one, when the cavity is filled 95%, and the other one is filled 98%. The one you saw before was like we assume that the entire cavity is filled. So when we change the filling, okay, so what we say is for varied temperatures and for this particular filling, so it's also showing now the porosity map. So again, my quality is fixed over here. So this is one way to see. The other way to see is also like based on all your simulation results, it is able to say that certain samples will have no porosity and certain samples may have porosity. So depending on all these permutation combinations which it is done, and it is now telling that this is the temperature. Somehow it says that the temperature has more influence than the filling, at least on what is selected over here. And with this temperature, it says that when you are below here, below this temperature, you have more possibilities to get a quality which is not acceptable for you, while when you are above this temperature, you have more possibilities to get the quality which is acceptable. So intuitively, I mean, to simplify, what is also possible to do is like just select what is our acceptable things, and it is going to plot all the simulations. So with both 95 and 98. So let's say we consider that we are going to pour between 95 and 98 or even 100, and it says that the process window is this one. So if we look at the first process window on this one, so there is a slight change over here because there was another parameter which was varied. So like this we can introduce more and more parameters. In casting we have a lot of variations and study what would happen with all these variations. So this will enable us to somehow know to predict the variableness of a foundry of a casting process, and then understand the design robustness of what is developed for this particular part. So finally, I mean, the philosophy of ESI is not just to make simulation to predict certain manufacturing processes and to predict defects in advance, but to also enable our users to manufacture or to simulate the parts as built. So which means that the influence of the manufacturing quality on the part performance is certainly there, and it's important to predict a simulation result which could probably be considered down the manufacturing line. For example, the casting part could be heat treated, so it's important to connect these two, and these can further be connected to other kinds of simulations. You also saw presentations from other colleagues today. So where, for example, this is a classical crash analysis, so it's important to consider the effects of manufacturing over here, because manufactured part is never homogeneous in its properties. So with this I end my presentation. So I leave the contacts of my colleague Ronan, who is based in the UK. Thank you very much for your attention. So if you have any questions, so we are here to answer.
both Ronan and Badarinath for their presentation. I think anybody who works in the Foundry, and I hate to admit that I've actually been in the Foundry industry for 30 years this year, I think it's very fascinating the benefits that we get from casting simulation and the savings that it makes, and you know, the ability to get it right first time. It isn't magic, it is a much more precise science these days than it's ever been, is what I see from my point of view. And I would like to invite questions from the audience, please. Go on, Chris.
Yeah, I'd like to know how the correlation of the pouring temperature, the die temperature, and the analysis of the data is done by the software. Does it take all these into consideration and then tell you a window in which you can operate? Is that what you were putting across there in those last few slides?
Yes, yes. So in fact, like, I mean, normally what happens is like when you make a simulation, you need to input your parameters. The parameters are the process conditions. You input these parameters. But what happens on the shop floor is these parameters can vary. So we cannot control the temperature exactly to a certain temperature. So over here, what it does is like it allows you to change these parameters. So this is considered, and then tells you for this variation how your casting quality is going to vary. Does this answer your question? Or?
I think so.
Okay.
Well, there's no other questions. Please join me in thanking both Ronan and Badarinath for this. Thank you.